Okay, now it's recording. So it's my pleasure to announce the next speaker. It's Calin Chindris from University of Missouri, Columbia, and he will talk about hive-type polytopes for queer semi-invariants and the membership problem for moment cones. So it's joint work with Brad Collins and Dan Klein. So please, Calin. Okay, Karen, you can start. We cannot hear you. Your microphone is off.
Can you hear me now?
Yes, now we can hear.
All right, very good. Yeah, well, thank you very much for the opportunity. I have very much enjoyed the talk so far. So I'll be talking about some combinatorial aspects of quiver semi-invariants and some applications to what's known as the membership problem to moment cones. These are rational convex polyhedral cones that arise from moment maps. And this is joint work with Brett Collins and Dan Klein. So let me begin with the motivation. So it goes back to a classical result, classical by now, I guess, by Knudsen and Tao. And late 90s, early 2000, they found a combinatorial description of the triple tensor multiplicities of tensor product multiplicities for the general linear group. And specifically, the quantities that they were looking at are defined as follows. So if you fix a positive integer n and a triple of partitions that have length at most n, by a partition I simply mean a weakly decreasing sequence of non-negative integers, and the length is defined to be the number of non-zero parts. Then the Liddell-Wood-Richardson coefficient associated to such a triple is defined to be, if you want, the multiplicity of this simple representation of GLV. So this is an irreducible representation of GLV. Here V is any vector space of dimension n, or at least n. For example, you can take V to be C to the n. And so the multiplicity of this irreducible representation into the tensor product of the other two, S lambda tensor S mu, is defined to be the Liddell-Wood-Richardson coefficient. And these are very famous fundamental structure constants. They show up in many areas, not only in mathematics, but outside of mathematics as well. More generally, if you have a sequence of partitions, lambda 1 through lambda sub r, these are all partitions of length at most n, then you can define the multiple LR coefficient, which is defined very similarly. It's defined according to this formula. And this multiple LR coefficient turns out to be, again, a single LR coefficient. And this is because of a very nice, neat trick, which is due to the late Andrei Zalevinsky. So you can express such a multiple LR coefficient as a single Liddell-Wood-Richardson coefficient, where the partitions mu1 and mu2 are chosen carefully. Specifically, for those of you who are familiar with the Young diagrams, the Young diagram of mu1 minus the Young diagram of mu2 has components which are precisely the Young diagrams of lambda 1 through lambda sub r. And so in 1999, Knudsen and Tao came up with the following result. If you have three partitions, lambda, mu, and u, they have size at most, length at most n. And if you assume that the size of one of them, so for example, the size of a partition, in this case, the size of nu is defined to be the sum of its parts. So once this very basic and necessary constraint is assumed, then the LR coefficient, the Liddell-Richardson coefficient corresponding to the triple of partitions, can be expressed as the number of integral points of a polytop. And the good thing is that this polytop can be easily visualized. You can draw it geometrically, and is known as the hive polytop. In more specific terms, the LR coefficient can be expressed as the number of integral hives. I'm going to explain what it means in just a bit, for which the boundary labels are fixed, are set. Specifically, they are determined by the parts of lambda, mu, and u. Yeah. And so instead of going through the definition of a hive, let me just explain it by means of an example. So let's take NB2. And the way to visualize this polytope is to start with with an equilateral triangle. You plot n+1 points on each side. So in this case, exactly 3 points on each side. And in this way, you get n squared. In this case, 4 smaller equilateral triangles, which are all of the same size. And then you begin labeling the sides of the smaller equilateral triangles by these numbers, E, F, and G. The EIJs, as you can see, they label the sides of the smaller equilateral triangle that are parallel to the left boundary. The Fs label the sides of the smaller equilateral triangles which are parallel to the right boundary. And then the Gs label the sides which are horizontal. Yeah, and these E, F, and G, they must satisfy what are known as the triangle and the rhombi inequalities. So what it means is that for every elementary triangle, and there are only 2 elementary triangles, no matter what n is, this is one elementary triangle, and this is the other elementary triangle. What you impose is that the length of the horizontal side is the sum of the other 2 lengths. And then there are also 3 types, again, no matter what n is, of rhombi. This is one kind. This is another kind. Yeah, and the third one and the last one looks like this. And again, there are some inequalities that the lengths of the sides must satisfy. In this case, as you can see, given that the boundaries are all fixed by the values of the parts of the partitions, just working with the fact that all these small elementary triangles must satisfy the identity that I just mentioned, you can see that, for example, G1 0 is a sum of lambda 2 and mu 1. And in fact, you can completely determine the values of E, F, and G in this case. And what it means is that when n is 2, the LR coefficient can be at most 1. Yeah. And so let me explain the relevance of this result. And in fact, the motivation for both Alan Knudsen and Terry Tao had to do with what's known as the Horn conjecture on the possible eigenvalues of a sum of 2 Hermitian matrices. And it turns out that this hive model, this combinatorial description of the LR coefficients, led to the first proof of what's known as the saturation conjecture for the LR coefficients. And what this conjecture states is that C lambda mu nu is non-zero if and only if you pick any positive stretch factor, call it L, and if you stretch each partition by such a factor, the corresponding LR coefficient is not 0 as well. And so this is actually not at all easy to prove. It sounds like an innocent statement, but it took quite a bit of time to prove it. And later on, Bill Fulton realized that Kryachko's work on Horn's conjecture, combined with this saturation conjecture for LR coefficients, leads to the proof of Horn's conjecture, which was posed in 1940. And this Horn conjecture was finally proved in 2000. So it took quite a bit of time to prove it. But the saturation conjecture, which relies in an essential way on Knudsen-Tao hive model, was a fundamental step. Yeah. And recently, in the context of algebraic complexity, the hive model, this very explicit, simple combinatorial description of the LR coefficients, combined with the fact that the LR coefficients are saturated, was used by Mulmule, Narayanan, and Sohoni to provide a strongly polynomial time algorithm to test the positivity of the LR coefficients. And so in theory, this is a good thing. But practice is a different story. Let me point out at this moment that if you have lambda mu and nu, there is an effective algorithm to compute the value of the LR coefficient if and only if P is NP. Yeah, and so computing the precise value of the LR coefficients is believed to be like an impossible task. However, to test their positivity can be done quite effectively. Let me also point out that the positivity of an LR coefficient is equivalent to saying that the triple of partitions, lambda, mu, and nu, does lie in a rational convex polyhedral cone known as the Klyachko cone. And this is defined to be the set of all triples of weakly decreasing sequences of n real numbers, such that there are 3 Hermitian matrices, with one of them being the sum of the other 2, and such that their spectra is being prescribed by the parts of lambda, mu, and nu. And in fact, describing in a certain way this rational convex polyhedral cone is known as Horn's conjecture. And let me switch gears a little bit, and this is because Maciej already talked about quiver semi-invariance. Let me point out that any LR coefficient, I'm gonna be more specific in just a bit. Any such LR coefficient can be viewed as the dimension of a weight space of semi-invariance, as was already defined in Maciej's talk. For a suitable quiver Q, dimension vector beta, and weight sigma. And in this general context of weight spaces of quiver semi-invariant, the saturation property holds again. And this is due to work of Derksen and Weyman. And their proof relies on what's known as the first fundamental theorem for quiver semi-invariance. And this first fundamental theorem in the quiver context was proved by Domokos and Zubkov, and Derksen and Weyman, and more or less at the same time by Schofield and Van den Berg. And so our goal is, given a quiver, a dimension vector beta, a stability weight sigma, the goal is to find an explicit polyhedral description of the dimensions of the weight spaces of quiver semi-invariance. So let me switch gears and talk about quiver representations. In fact, I won't touch quiver representations, but let me very quickly introduce this quiver semi-invariance. So a quiver, we already saw this morning, is just a directed graph. It has a finite set of vertices, a finite set of arrows, and then there is a tail and head function. They assign to every arrow its tail and head respectively. A dimension vector is just an assignment of non-negative integers to the vertices. I assume that the dimension vector is sincere, meaning that all coordinates are positive. This is something that Maciej already mentioned as well. And once you fix this very basic numerical invariant, just a dimension, it makes sense to collect all the representations of Q that have dimension vector beta and construct this affine space in this case, because we have no relations. And this is defined to be a product of spaces of matrices. This is a product over all arrows A of the space of matrices of size, the dimension vector beta at head of A by the dimension vector beta at tail of A. And this vector space, this affine space, comes equipped with the natural action by simultaneous conjugation of the base change group, GL beta. And this is defined to be just a product of general linear groups. And the action is the obvious one by, as I said, simultaneous conjugation. So So I believe that Maciej mentioned that if Q is acyclic, then the action of GL beta on this representation space is rather boring, because it leads to only constant invariance. However, if you twist this action by means of a character, namely a stability weight, by which I mean an assignment of integers to the vertices of the quiver Q, which can be identified with the group of rational characters of GL beta, then the resulting action leads to some highly non-trivial objects. We have seen already these moduli spaces of quiver representations. But in this talk, I will focus on the combinatorics of the graded pieces of the graded algebra whose proj defines the moduli space that featured in Maciej's talk. So this is how we define a weight space of semi-invariant. So the quiver Q and the dimension vector beta is fixed. Let's fix a character by equivalently a stability weight sigma. And the space of semi-invariance of weight sigma is then defined to be the space consisting of all regular functions f, for which the action of any group element G on f is given by the scalar multiplication of f by the value of the character at G. And so for concreteness, this is how the character induced by sigma looks like. And so it turns out that these spaces have a very rich combinatorics on top of the geometry that they have. Let me give you an example. This example explains how to view any Littlewood-Richardson coefficient as a dimension of a weight space of semi-invariance. Okay, so again, let me fix a positive integer n. Let me fix a triple of partitions, lambda, mu, nu. Each has length at most n. Given n, you can construct the quiver Q, which looks like a star or flag quiver. So you have this central vertex, and there are two flags going out and one flag going in. By a flag, I really mean I mean this type of equi-oriented type A quivers. And you have exactly n vertices along each flag. And the dimension vector then is defined to be 1 through n along each flag, just like that. And so Q and beta depend only on n. Now, if you give me a triple of partitions, I can write down a stability weight, or if you want, a rational character for GL beta. And the way you define it goes as follows. So along the first n-1 vertices of this flag that goes out, you assign non-negative, you assign non-positive weights. So note that these are all non-negative. Along the first n-1 vertices of the flag that goes in, you assign these weights, which are all non-positive, because we are dealing with partitions, which are weakly decreasing sequences. And then at the central vertex, to make things work the way we want, you assign this particular integer. And so this is the weight sigma, which depends on lambda, mu, and nu. And then using some standard computations involving the representation theory of GLN, specifically Schur representations, the S lambdas, that is to say, that I mentioned at the very beginning of the talk, you can express the LR coefficient, C lambda mu nu, as a dimension of this weight space of semi-invariance. And so this rather simple computation, what it does is to allow to bring to bear methods from quiver invariant theory and the geometric invariant theory into the study of these combinatorial structure constants. Before I move on, let me introduce one other object, which I hope to have time to say something about it. So if you have a quiver Q and a dimension vector, the moment cone associated to this pair Q beta is defined to be the following rational convex polyhedral cone. So it consists of all tuples of weakly decreasing sequences. So for every vertex vertex x of Q, lambda of x is a weakly decreasing sequence of real numbers. And what we want for this tuple is to be so that there exists a representation, or if you want, a tuple of matrices W of A, one matrix for every arrow, where W of A has the right size, such that the spectrum of this Hermitian matrix is exactly lambda of x. So S of a Hermitian matrix stands for the spectrum of that matrix. And so, for example, if you take Q to be just this bipartite quiver that has one source vertex and two sinc vertices, and if you take beta to be this dimension vector, then this moment cone is essentially the Kryachka cone that's related to Horn's conjecture, which in fact goes back to 1912 to Hermann Weyl eigenvalue problem for the sum of two Hermitian matrices. All right, and so as I said, our goal is to find a combinatorial description, a polyhedral description of weight spaces of quiver semi-invariants. And we also want to relate that to the moment cone, just like the Lieder-Hutchinson coefficients their positivity is related to whether a certain triple of partitions lies in the Kryachka cone. And we'll perform the following little trick. So if you have any quiver setup, which consists of a quiver Q and a dimension vector, we insert a flag of length beta of x minus 1 at every vertex. By the length, I mean the number of arrows. And in this way, we get the flag extension Q tilde beta tilde of the initial quiver setup Q beta. And so what happens is that there is an isomorphism between the moment cone associated to Q beta and this cone of effective weights. And let me just say that this cone, or at least the lattice points of this cone, are defined as follows. So you have a sigma tilde, which is a stability weight for Q tilde. And this is a lattice point of the cone of effective weights if and only if the dimension of the corresponding weight space of semi-invariants is positive. So these cones of effective weights show up in GIT and the variation of GIT quotients, but they also have very beautiful combinatorics. And so to test whether something lies in a moment cone really comes down to checking whether a weight space of semi-invariants is positive. So for example, if you take Q to be this quiver setup, so Q again is the quiver from the previous example where you have, which is a bipartite quiver, you have only one source vertex and two sinc vertices. And let me take beta this time to be n at the source and n minus 1 at the sinks. And then the flag extension of Q beta looks just like this. You just insert flags of appropriate length. And you also extend the dimension vector beta tilde along the flags in the most natural way. And if you would recall, this is exactly the quiver that we encountered when we computed the LR coefficient and showed that an LR coefficient can be viewed as a dimension of a weight space of semi-invariants. All right, so now let me write down one of our main results. So this is about hive-type polytopes for quiver semi-invariants. Our goal was to find an explicit polytopal description, not just some abstract polytopal description. And so we were able to do it for quivers that we refer to as incomplete bipartite quivers. So you have a bunch of source vertices and a bunch of sink vertices, and between any source and any sink, you have exactly n arrows. You know? And that's right. And so there are many wild quivers which are of this form. And let me pick a dimension vector beta as well. And we assume that beta is sincere. If it's not, then if beta is 0 at a vertex, we just erase that vertex and all the arrows that have anything to do with that vertex. And then we consider the flag extension of Q and beta, which looks like this. Yeah, you just insert the flags that go into the source vertices and go out of the sink vertices. And you extend the dimension vector beta to beta tilde in the most obvious way. And then what we proved is that if you have any stability weight, sigma tilde, of this flag extended quiver Q beta, and this is just a technicality. And if sigma tilde is assumed to be non-negative along the flags that go in, and non-positive along the flags that go out, then we were able to compute and express the dimension of the corresponding weight space of semi-invariants as the number of lattice points of a polytop. And this polytop is actually obtained by gluing together only two Knudson-Tao hive-type polytops. So this triangle is a hive polytop as defined by Knudson and Tao. These two sides, which are labeled by gamma 1 and gamma 2, the sides of the lengths of all the sides that lie along those two bigger sides are fixed by the parts of gamma 1 and gamma 2. And then you have this other hive model, which is a triangle upside down. And what we did was to glue these two hive polytops along this common side. And in this way, we get this polytop, whose boundary is fixed by the parts of these partitions, where these partitions can be combinatorially derived from beta tilde and sigma tilde. And the number of lattice points turns out to be exactly our weight space of semi-invariants. So I believe I have 2 more minutes. Let me just make some very quick comments. So about the proof of this result. So if you compute the dimension of the weight space of semi-invariants for this particular quiver and dimension vector beta tilde and weight sigma tilde, if you compute it directly using Cauchy formula and the basic representation theory of GLN, you end up with a humongous sum over very many partition variables, where each term is a huge product of multiple Liddell Richardson coefficients. So the result is just incredibly complicated. It's almost impossible to visualize it. And so what do you do? Well, what we did with this particular quiver was to use a technique which is known as, which is based on quiver exceptional sequences that allowed us to embed this quiver into something simpler, significantly simpler, and this embedding actually preserves the dimensions of weight spaces of semi-invariants. And so this allowed us to focus on a quiver which looks a little bigger, but it's much easier to compute their dimensions, the dimensions of their weight spaces of semi-invariants. And in the end, we ended up with this description, which can be written as just a sum of only of a product of only two multiple LR coefficients. And it is precisely this this formula that allowed us to come up with this combinatorial model, which is somehow constructed in the same vein as Knudsen-Tower hive model. So I think that my time is up, if I'm not wrong.
Okay, so did you finish? Or if you want, you
Yeah.
can talk for another 1 or 2 minutes. Okay, so you finished, yes. Okay, so let's thank the speaker again. Okay, and are any questions or comments? Okay, Becky.
So, what was the motivation to consider this complete bipartite river?
Yeah, the motivation is that was that it was the only one where we could compute things. So pretty much. So I mean, the idea is to given any acyclic quiver, dimension vector beta and sigma, the long-term goal is to come up with a polytopic description for the dimensions of the weight spaces of semi-invariants, just like Knudsen and Tower did with LR coefficients. But it's only the this bipartite quiver that somehow we were able to embed into something that's more manageable. But I mean, we would like to extend this to any quiver, though. But it seems to be very difficult.
Thank you.
Yeah.
Marius, do you have other questions?
No, at the moment.
Well, there was a question of Becky.
Sorry, I don't have a question.
Okay. And so no more questions? Comments? Okay, then let's thank the speaker again.